Welcome back to the series where we are coding an app to solve the board game Clue. In this video, the rubber hits the road. Picking right up from the last one, we'll end up with the data structures and algorithms we need to code the core logic. We'll build our code piece by piece, and you'll be able to understand exactly what's going on and why, no matter your level of coding experience. In the previous video, we thoroughly understood the problem space. We learned the rules of the game, explored the deeper logic, and developed a better strategy for playing, including a notation system to keep track of our knowledge, and a procedure we can use to deduce more knowledge and solve the murder before all of our friends. In this video, our main focus is forming a crystal clear, detailed plan for building this clue solver. The data structures we need to represent knowledge, the algorithms we need to deduce more knowledge, and any objects we need along the way to model the game. Basically, we're getting more detailed on those consistency and deduction rules from the previous video. Click the link up here in case you missed it. We'll jump back and forth from whiteboard to keyboard as we build things out, and start at the whiteboard to form a little bit of a plan. Oh, can't we just start coding now? I actually kind of love planning on the whiteboard, because we're effectively writing code, but it's a lot easier. We're taking the time to understand exactly what we're doing right now while they're still easy to change. But I understand if you disagree. I promise you by the end of the series, jumping back and forth between whiteboard and keyboard will feel natural and valuable. It's a great way to level up your career, so it's a good skill to learn, and I may even convince you that it's actually fun. Alright, with that said, let's get into it! So from a technical standpoint, what is the core logic at its essence? Effectively, the core logic will be a function that takes the knowledge we know now, transforms it using some algorithms to spit out the knowledge that we've learned. We'll need to figure out some data structures to actually represent that knowledge, and what those algorithms actually are to spit out the new knowledge, which together I'll name the Deducer, because it sounds funny. So since knowledge is at the core of this whole thing, let's start by figuring that out. Let's do a quick recap of the previous video's notation system. We had the main checklist with columns for each player going across the top, and rows for each card going down the side. We tacked on another row for the case file specifically, and one thing we forgot in the last video was how many cards were in each player's hands. The shrewd ones among you might remember that some of our consistency rules depended on how many cards were in each player's hand, so we're going to need that information from the user. So when we're interacting with this checklist, we either read from it or we write to it. For example, if we were playing with Anisha, Bob, and Cho, and we wanted to look up our information about Anisha and the wrench, we'll find the column for Anisha and the row for the wrench, and read the value in the cell, either a Y, an N, or a blank, meaning we don't know. Similarly for the case file, if we're interested about a particular card, we find that row in the case file column and we read the value of the cell, either a Y, an N, or we don't know. And of course, along the bottom, we can look up the number of cards in any particular player's hand. And we can alter the checklist by doing the same thing and writing a value into one of the cells. So to me, right off the bat, this screams for a map. You can think of a map as just a box of key value pairs, where you can ask it about the value for a particular key. This box will hold that data in a structured format, hence data structure. For the player checklist, for example, the keys would be player card pairs, and the values would be Y, N, or unknown. And one immediate optimization we can make is to not save any values for the unknowns, and I'll show you why in a second. So the first thing we can do is get a value out of the map. If we want to know about Anisha's ownership of Professor Plum, we say get Anisha, Plum, and it'll spit out the value. In this example, since it has Anisha, Plum stored as a Y, it'll give us back a Y. For a key value pair that's not saved in the map, say we ask it about Cho and the wrench, it'll spit out an undefined, saying, I don't know anything about this. And given that that's standard behavior for map data structures, we can use that to our advantage to represent we don't know. So there's no need for us to actually save a question mark in there. The second thing we can do, of course, is set a value, like writing into the checklist. So if we tell this map set Cho, wrench equals Y, it'll save that value. Then the next time we ask it about Cho, wrench, it'll give us Y instead of undefined. So our knowledge basically has three maps: a map for the player checklist and a map for the case file checklist. In this case, we know we're looking up in the case file, so we don't need to give it a player. So the map is just from card to Y or N. And last, we want the user to supply us information about how many cards are in each player's hand, and that'll be a map from a player to a number. Okay, so let's finally jump to the keyboard to check out the project and see how we would define knowledge in code. Okay, so opening up our app, you can see here that we have Oh wait, you can't see this, huh? Let's fix that. And now that that's fixed, welcome to our code. This file lists out all the cards in the game and all the players we're playing with. And it brings up an important point. There will be some extra stuff in here, so I want you to really focus on just what I'm calling out. Over here in our knowledge file, we have the definition of knowledge that we outlined on the whiteboard. It's a player checklist that is a map from player and card pairs to Y or N, a case file checklist that is a map from cards to Y or N, and player hand size, which is a map from players to numbers. Like I said, there's some extra stuff around here, but just focus on this for now and see how much it matches exactly what we wrote on the whiteboard. So now that we know what data structures we're using to represent knowledge, let's move on to some of the algorithms. So we'll break that down like we did in the last video into consistency rules and deduction rules. Let's start with the consistency rules. So consulting the previous video, these are all the consistency rules that we found. Smart guy. Let's start with the rule that a card is owned at most once. That's going to be the easiest one to do first. So as a quick refresher, what is this rule doing? Basically, in the checklist, if we see a Y somewhere in a row, we should change all the other ones to N's. It signifies that only one person can own a card, which is obvious. So in order to make this an algorithm, let's really break down the steps we use as an actual human when we're executing this consistency rule. So what are we doing? We're basically scanning the checklist row by row. For each row, we go through every cell to see if there's a Y in there. If there's not, then we move on to the next row. If we do encounter a Y, then we go back through that row and change every blank cell into an N. So let's write that out as an algorithm. For each card, which we'll call C, we check if some player has a Y using our player checklist map. If that's the case, then we go through for each player in that row, call it P, and set P, C to N. We are simplifying a little bit. For example, to check if some player has a Y in that row, we're basically looping for each player, check if there is a Y, but this is pretty good for now. Once again, let's jump to the keyboard and see how we would write this. And here we are back in code. We can move into our consistency rules file, where we've defined a consistency rule as a function that takes in knowledge and returns knowledge. And here's our consistency rule that cards are owned at most one time. It takes in our initial knowledge, goes through each card, checks if some player owns that card. It does that by going through every player and checking whether the value in the player checklist for that player and card is exactly equal to a Y. If that's true, then is owned by some player will be true because some player owns that card. Next, we're kind of flipping the check as we wrote it in the whiteboard. Here, instead of checking whether some player owns the card is true, we actually check whether it's false. If that's the case, we return early from the function with no new knowledge. Continuing from there, we now know is owned by some player is true for the rest of this function, meaning that some player does own that card. We then update our knowledge. Going through all the players, we update the knowledge by modifying the player checklist to set that player and that card to an N. And always when you're writing code, you should write some automated tests to make sure that that code is doing what you think it's doing. A test basically involves giving some input to the function, taking what comes out of it, and checking that that is what you expect it to be. So let's write the following test for this consistency rule. For our knowledge in, we'll set a couple values in the player checklist and leave the case file checklist and player hand size map empty. In the player checklist, let's say that we know Anisha has the wrench and Cho has the revolver. So what knowledge do we expect to get back out of this consistency rule? Well, we're not going to learn anything about the case file or the player hand size, but for our player checklist, we'll get a few new bits of information. We'll still have that Anisha owns the wrench, but now we'll learn that Bob and Cho both do not own the wrench. Similarly for Cho and the revolver, she still has it, and now we'll learn that Anisha and Bob do not own the revolver. So let's get back to the keyboard, write that test up, and run it. And now we'll move from the definition of our consistency rule over to the file where I've written the test. I've named this test, Some Cards Are Owned by Some Players. In it, we define our initial knowledge. In our player checklist, we say that Anisha owns the wrench by setting Anisha, wrench to a value of Y. We say that Cho owns the revolver by setting Cho, revolver to a value of Y. we leave the case file checklist and the player hand size checklist maps empty. We then give this initial knowledge to our consistency rule and get out the new knowledge. And the last thing we do is expect that this new knowledge is equal to this value. Our knowledge out should still have that Anisha owns the wrench, Cho owns the revolver, and that Bob and Cho do not own the wrench, and Anisha and Bob do not own the revolver. Let's see if that works. This little red squiggle tells us that it's already run the test and we did not get the knowledge we expected. Here are the differences, and I'll translate that back at the whiteboard. And oops, it didn't pass. Of course it does, it never does the first time. But what happened? For some reason, we flipped Anisha's ownership of the wrench to a no, and Cho's ownership of the revolver to a no. Looking back at our algorithm, can you spot why that might be? And you'd be right, it's this line right here. What we actually wrote was, if there's a Y somewhere in the row, go back through the row and replace everything to an N. That's not what we want. Adding a little check to make sure that a cell is blank before we actually update it will fix that issue. Going back from our failed test to the definition of our consistency rule, let's hide the shame. As we identified on the whiteboard, down here, we just updated every single player to a value of N. To fix that, we should skip the blanks. So let's add this little check here. We get the value for a player, and if it's not undefined, then we short-circuit the function, returning the knowledge we have right now. For any player card pairs where we already have a value, we will just return our existing knowledge, and we will not update the knowledge to set the value as an N. Now let's save this and see if our test passed. Back over at the test, let's scroll up, and hey, it passed. Hold up, there's actually an error in one of these tests, and maybe you can see what it is. If you want to explore that algorithm in more detail, including with more tests, we can figure out what that issue is in this bonus video. Check it out now and come back here when you're done. Okay, so we just defined that consistency rule. Let's take a step back for a second. Consistency rules are one of the two types of algorithms. They take in knowledge that we know and return updated knowledge, including new learnings. Deduction rules will be slightly different. If you remember from last time I said deduction rules, these concern the suggestion log at the bottom. So deduction rules will additionally need all the suggestions as input. So real quick, just like we did for knowledge itself, let's decide what a suggestion actually looks like. This is actually pretty simple. A suggestion is defined by a few different properties. The suggester, which is the player who made the suggestion, the cards, which is the set of cards that they suggested, the non-refuters, which is the set of players that were given the chance to refute it but were not able to, the refuter, which is the player who refuted, or undefined if nobody was able to refute the suggestion, and the seen refute card in case you actually physically observed the card that was used to refute that suggestion. Noting a few things, ultimately we'll be asking the user to fill in all this information, and they'll have to explicitly tell us who all the non-refuters were. This makes it easier for our app because we don't need to keep track of which order they refuted the suggestions. We'll just ask the user to give that to us directly. And just to be clear, if a suggestion was unrefuted, both the refuter and the seen refute card would be undefined. If the suggestion was refuted, but we did not see the card that was used to refute, then the refuter would be defined as the player, and seen refute card would be undefined since we don't know what it was. So that encapsulates all the information we need about a suggestion and all the states that a suggestion could have. Okay, so finally we can jump into deduction rules. Doing our homework, the previous video says. So our list of deduction rules is as follows. Let's first start with the super easy deduction rule that non-refuters don't have any of the cards. When we're going through the suggestions, for every player we find who passed on refuting, we should go through all the cards in that suggestion and set that player's ownership to N in the player checklist. And that's it. First, let's look at the definition of a suggestion. In this file, we've defined suggestion to be exactly what we wrote on the whiteboard. Then, jumping over to our deduction rules, we've defined a deduction rule as a function that takes a set of suggestions, the knowledge we know now, and returns some new knowledge. Here's our code for the deduction rule we just did on the whiteboard. Taking in the suggestions and the knowledge we know now, we go through every suggestion. We get every combination of non-refuters and cards, and iterate through them here. First, we check the player checklist. What do we know about this non-refuter and the card? If we do know something about this non-refuter's ownership of that card already, we just short-circuit the function returning the knowledge we have already. Otherwise, we continue because we have a blank. We then update the knowledge by modifying the player checklist to set the non-refuter's ownership of that card to a no. Again, I'll write some tests off screen, but let's move on to the much more interesting deduction rule, which is hard to give a name to. The refuter if we could eliminate 2 of the cards used the last card. What is this rule saying? So for each suggestion, if there is a refuter and we did not directly observe the card they used to refute, then if we are able to eliminate 2 out of 3 of the cards from that suggestion, then they must have used the third one to refute. Also, if we did directly see the card, then they definitely have that one. So for each suggestion, we first check if there's a refuter. If there is, we have 2 cases. First case, we saw the refute card directly, in which case we set that player and that card to a Y. Second case, we did not see the refute card directly, so we count the number of cards from that suggestion for which the player has an N. If that count equals the number of cards suggested minus 1, then for each card that was suggested, we set that player's ownership of that card to a Y if it was blank. We, the programmers, know that this rule will only ever set one Y at a time, but we have to go through the list of all cards to find that blank one to set it as a Y. So let's write this one as code. And back in Codeland, I convinced myself to split this deduction rule into 2. One for when we've seen the card that was used to refute a suggestion, and the other part, which I've given a much better name, the refuter used the only card they own. Check out the bonus video where I convince myself with some pretty good reasons why we should split this one up. Let's tackle these 2 one by one. First, the refuter used the seen card. We go through every suggestion. If there was no refuter or there was no seen card, then there's nothing for us to do. We need both of these defined for this deduction rule. If we already know in the player checklist that the refuter owns the card that was used to refute, then we don't need to update anything. If we don't know about the refuter's ownership of that seen card, well then we better set it. We'll update our knowledge, modifying the player checklist to set the refuter's ownership of the seen refuted card to a Y. Because of course they have that card if they used it to refute a suggestion. The second part of the deduction rule is the more complex part. The refuter used the only card they own. First, of course, we iterate through every suggestion. If there was no refuter, then we return early. Or if we saw the card, we also return early because that's what our other deduction rule is for. Then we count the number of cards that the refuter does not have. Going through all of the suggested cards, we check in the player checklist what we know about the refuter and that suggested card. If the value is N, we add it to our count, and our final count will be the number of N's that the refuter has for all the suggested cards. If this number of N's is less than the number of cards suggested minus 1, then there's nothing we can learn. We just return early with the knowledge that we already had. Otherwise, we can mark that remaining card from the suggestion as a Y for that refuter. To do this, we iterate through all the cards that were suggested. We check if this is the one that's blank. If it's not, then we return early. Otherwise, it's the blank cell, and we update our knowledge by modifying the player checklist to set the refuter's ownership of that card to a Y, because we figured out what they used to refute the suggestion. Okay, so backing out again, we are so close to landing this plane. Like we said at the very beginning, the deducer will take some knowledge and the suggestions, which will be needed by the deduction rules, and spit out some knowledge. We have all the algorithms for the consistency and the deduction rules. Now it's time to cram that all into the deducer. The deducer will tell us how to combine all those algorithms and figure out when we're done deducing. So the deducer will look something like this. On the left will be our inputs to the function. We have the knowledge we know, we'll call k_in, and the suggestions, we'll just call s's. The first thing we'll do is run that knowledge through all the consistency rules. We'll take that knowledge in, call it k1, and we'll first run it through the first consistency rule. This will give us some knowledge out, which we'll call k2. We'll take k2 and pass it through the second consistency rule, which will give us k3. We'll take that and pass it through the third consistency rule, all the way through the consistency rules until we finally get kn. Next, we'll do all the deduction rules. We'll take this kn and the suggestions, pass that through the first deduction rule, which will give us new knowledge, kn+1. we'll pass it through the second deduction rule, and so on and so forth until the last deduction rule will give us some knowledge which we'll call k out. And that's the knowledge we will have learned after running through all the consistency rules and all the deduction rules. But there's one more thing. You know I love a good reference to the last video, so let's see what we said. But we have discovered some new information, which means we might be able to deduce more. That's right. If we learn some new knowledge going through all these rules, we might be able to deduce new knowledge. So there's one last step we need to do. We'll take this k out and check if it's exactly the same as k1. What we're doing here is checking each of the maps in that knowledge to see if they have the same exact data. If they have the same exact data, that means we did not learn anything new, and we can just return that out of the deducer. If they are unequal, that means we learned something new, and we should pass it through all of the consistency and deduction rules again. We'll take this k out and pass it back through like it's the k1, through all the consistency rules, all the deduction rules, and get a new k out. We'll keep looping this until finally one of those loops doesn't yield any new knowledge, which means we have learned as much as we possibly can, and we'll return that from the deducer. So there we have it, we finally cracked the code. That's what's going on in that deducer. We're taking all the knowledge through all the consistency rules and deduction rules, looping if we need to, and finally returning out all the knowledge that we've learned. So let's take it to the keyboard. And now we can jump to the deducer file. Here we've defined the deducer just like a deduction rule. It takes some suggestions and some knowledge that we know now and returns some knowledge that we've learned. And here we've defined the algorithm we use. I made a promise to code this as cleanly as I would in real life, even if it doesn't match the whiteboard exactly. So here's some interesting tricks. This change relies on the fact that a deduction rule is almost the same as a consistency rule, except for the suggestions. Once you've given the deduction rule its suggestions, it looks exactly like a consistency rule. Since the deducer algorithm will eventually pass its suggestions directly into the deduction rules, we first quickly convert all the deduction rules into consistency rules by passing in the suggestions now. This means the deduction rules will basically just operate like consistency rules. So here we have a list of all the consistency rules, plus all of the deduction rules after they've been given the suggestions. Now, all of our rules just look like consistency rules. This will make the rest of the algorithm that much simpler. And yep, that's the whole thing. Now that we've loaded all the suggestions into those deduction rules, the deducer is much simpler. First, it takes our knowledge in. We run through all of the rules, updating our knowledge by passing it into the rule and taking whatever comes out. We set that to a knowledge out. We continue doing this as long as the knowledge out and the knowledge in, aka K1, are not equal to each other. If they're not equal, we go back here, set our knowledge out back to knowledge iteration in, aka K1, and use that as the basis for our next iteration through all of the rules. We apply all of the rules, get a knowledge out, check if it's equal, and keep doing that until finally the knowledge out and the knowledge iteration in are equal, at which point we return our knowledge out. I think what's so interesting about code is it packs into these 15 lines that whole flowchart that we wrote out on the whiteboard. Isn't that so cool? So that's all of our core logic written on the whiteboard and in code. And that's how an experienced software engineer would break down problems, come up with the data structures and algorithms to solve them, plan things on a whiteboard, and write them in code. I hope you enjoyed this brief practical introduction to data structures and algorithms, and you were able to understand all the code snippets that we showed. I really enjoyed how systematizing the strategy in the last video made it a lot easier to come up with the algorithms in this video. There are so many more exciting iterations of this project to come, different phases of software development, different concepts, different engineering principles. It's only going to get way more exciting from here. I'll drop a link to the code in the description so you can check all that out. Let me know what you think in the comments, and don't forget to subscribe so you don't miss the next video. I know I can't wait to get to the next one, but I want to know what you want to see. So until then, bye-bye. A lot of work goes into planning, scripting, filming, and editing these videos, not to mention actually programming the project. So if you'd like to support me as I make more, that would be greatly appreciated. The link to my Patreon is in the description.